I haven't verified yet. Just had a student here coming up, pointing out in the example we did in the previous lecture, this example here, solving this second-order homogeneous linear ODE, which has a characteristic equation like that. And in my lecture, I wrote it down. The complex conjugate solution is -0.2 plus minus J3, and possibly that's over here should be 3 over root 2. So I need to verify that. Okay, you can try yourself. That might be a mistake. Okay, this is exactly what I want. If you see any mistakes, let me know. Okay, and then I can improve my lecture notes. Okay, so let's continue the lecture here, okay, on free vibration. By the way, the midterm marks were uploaded. Okay, the TA has helped me upload all the grades. And so I have the paper in my office, but I haven't sorted it out yet. In order to return it back to you, I will sort it according to the last name, and hopefully I'll give it back to you on Friday. Okay, yeah, but the challenge, as you probably see, is once I finish the other lecture, and I carry all the papers over here. Right? It's a lot of work. Okay. Anyway, Friday is the object of the target. Okay. Just a quick review of what we did in the previous lecture. Okay, so we finished linear homogeneous second order ODE, and I introduced basically the applications of that. So bearing in mind that what you're seeing here is, okay, it's just a different perspective. It's basically relating differential equation, homogeneous one, with an actual system. So we use a mechanical system, mass spring damper system, to illustrate the idea. And you can certainly use any electrical system or something else, okay, to illustrate the idea. Okay. So the first type of system is the so-called undamped system. When you have a mass and a spring system like that, so there's no damping, right? So this is why they call it undamped system. For undamped system, for this kind of system, if you have an initial, for example, you push down a little bit, and then you let it go, so that mass will keep vibrate basically. Okay? Yeah, because there's no damping here, so it will just continuously vibrate. Okay? This is going to be the X here. Now, in terms of mathematically, this is the model for the mass spring system, second order, linear homogeneous ODE exactly, because there's no external force. And after this lecture, we'll learn what happens if we have external force. Then the characteristic equation is m lambda squared plus k equal to 0. And you have two complex conjugate roots. So basically, it's like a positive negative g is this square root of k over m. The solution will be a times cosine this t and b times sine this t here. So we can define this square root k over m as the so-called natural frequency. So this is the idea. I want to give you an idea, between this real system and pure math. So the omega n here is the root k over m, and which is called natural frequency, because apparently the sinusoidal will vibrate at this frequency. Okay? At a different, of course, E can be calculated based on initial condition. Okay, and phi also can be calculated based on A and B. If you have an initial condition, you also be able to calculate phi. Okay. So that's undamped system. You have a constant vibration with this frequency. So in the future, you actually will be able to tell if you're given a second order linear ODE like that, and if the question is, what is the natural frequency of the system? So what do? You basically calculate root k over m to get the natural frequency. Right? Now, second case is when you have free vibration, so no external force, but this time you have this viscous damping in it. Okay, so there's a damping B at here. Then the second order equation, or the model of the equation is a second order. So mx double dot plus bx dot plus ckx equal to 0. Right. So we show this in a different location, different part of the lectures. Characteristic equation m lambda square plus b lambda plus k equal to 0. Solution of this characteristic equation has lambda 1, 2. So basically the same format as you have A, B, C, right? In the table that give it out to you. Okay. So the lambda here, right? The value of the lambda, then you have, if you recall that, then you have 3 different cases. So 2 real, 2 repeated, and 2 complex conjugate. Okay, depending on the value of m, b, k. Right. So now there's nothing new at here, right? So what I do at here is I do want to introduce this different perspective from mechanical system point of view here, okay, or simply from the vibration concept. Okay, so we introduce at here, okay, instead of using m, b, k, okay, we're going to introduce a new set of parameter. The first parameter introduced is the so-called natural frequency. Right, that's like in the first case, square root k over m. And the second parameter introduced at here is called the damping ratio. So damping ratio is defined as damping constant B divided by critical damping constant. You'll see why it is called critical. Critical damping constant is defined as BC equal to root 4mk. So basically, if you look at the solution for the characteristic equation here, you got to square root something. The values underneath the square root, right, is the key factor determining whether you have real roots or whether you have complex roots. So if this value here is less than 0, you get complex roots. If this value is greater than 0, then you got real roots. And if this value is equal to 0, then you actually get a repeated roots, right? So that's basically why this term is important. So this term b squared equal to 4mk, which is essentially b equal to 4mk, that's how we define the square root of 4mk as the so-called critical damping constant. Okay, so basically we introduced an omega n and the damping ratio zeta. Okay, 2 variables. Okay, and these 2 variables are functions of MBK, right? The original system parameter, mass, spring, and damper parameter. Okay. So what do we do from here then, right? What do we do from here is we will still go through exactly the same approach here. So your original mx double dot plus bx dot plus kx. Okay. This is your original second order equation. Okay. If I divide it by m and here, okay, we'll get this equation here. And now I can make use of the newly defined omega n and zeta to replace those m, b, k. So basically, as you can see, the x at here, the coefficient for x, instead of a k over m, it can be replaced with what now? Omega n squared, right? Omega n squared. And the coefficient for x dot, which is b over m, that can be replaced with 2 zeta omega n. And if you don't believe it, you can do this. You say, what's 2 times zeta times omega n? Because this is zeta here, right? 2 times b over 2 km. And omega n is k over m. Okay. So if you multiply all of this out, and you get b over m. So basically your original linear second order differential equation, we use a new set of parameters to write it. Okay. Theoretically nothing changed. Okay? Nothing changed here except we're using a new set of variable. The reason is because in the third year, and when you're learning vibration, and you'll see this is the standard format for studying vibration system: natural frequency and damping ratio zeta. Okay, those are two standard parameters in study vibrations. Okay. So basically, any given second order ODE, right? Like even like ABC, whatever you give in here, you can always write it into this format in terms of omega n and damping ratio. Okay. So we'll give the system a different perspective in terms of omega n and zeta. Now the solution of the characteristic equation for this second order system in omega n and zeta can be solved, okay, as this. So you got basically two solutions, okay, for this quadratic equation in terms of zeta omega n now, okay, instead of ABC or instead of NDK. Right? Okay, so this is your solution of the characteristic equation. And again, the solution for the lambda has three different cases, okay, very much like the other case. So first, you could have when zeta square is greater than 1, okay, or when zeta is greater than 1. Okay, that's the first case. And when this is greater than 1, the lambda here are what? You got two real roots. Okay, two distinct real roots. Okay, so that's what you're going to get. Okay, so when zeta is greater than 1, you get two distinct real roots. Okay. Lambda 1 equal to negative omega n plus omega n zeta squared minus 1. Lambda 2 equal negative zeta omega n minus omega n zeta squared minus 1. Okay. All right, that's specifically the two solutions at here. Okay. So if you look at the two solutions for lambda 1, lambda 2, let's look at the lambda 2 here. Okay, negative, negative, and omega n and zeta, they are real numbers. They are basically system parameters, so they cannot be negative numbers. So basically means lambda 2 must be a value less than 0, right? Okay. And lambda 1, you have the first term plus the second term. Okay, so that's plus the second term here. And you could do a little bit of simplification here. If you look at the second term, this is a zeta squared minus 1. Now if I get rid of the negative 1, if I only have the negative zeta squared, so this zeta here must be less than zeta squared minus 1 square root must be less than this one. Okay? So in other words, this term must be less than this. Okay. And this happened to be 0, this plus this. So the basically lambda 1, what I just showed you here, is also less than 0. So both lambda 1 and lambda 2 are less than 0. That makes sense? Right? So then what's the solution for our system? We use our table, right? So you have the second order ODE here, and you have your lambda 1, lambda 2, and the solution for this system is C1 e times lambda 1t plus C2 e to the power of lambda 2t. Okay? That's a general solution. So general solution for second order linear homogeneous ODE. Okay. So why am I showing you both of lambda 1, lambda 2 less than 0? Because of this. Look at this. This is a solution here, right? So what happens to an exponential function whose coefficient is less than 0? Go to 0. So that basically means as t go to 0, your x of t will go to 0. Okay. Does that make sense? Because what a system we're studying here? We're studying mass spring damper system. So you do have a damping. So even though, let's say you pull it a little bit, right, give it an initial condition, let it go. It will vibrate, but as the time goes on, it will settle down, right? So that's basically when x of t back to its equilibrium position. And this shows you exactly why. Okay. In this case, it will go to 0. Because lambda here, I just showed you both lambda 1, lambda 2 are less than 0. So it's like a e to the power negative 0.5 t and e to the power negative 0.4 t, for example, right? And what does it go? It will go to 0 as t go to infinite. Okay. So the mass confirms with the physical system, right? Okay. And for this system here, for this case 1, remember what zeta called? Zeta is called damping ratio, right? And this damping ratio in this case is greater than 1. So in this case here, when damping ratio is greater than 1, we call it an overdamped system. So it's overdamped system. It will go to 0. That's actually what the overdamped means. Okay. So x of t, if you draw x of t, if this is x of t, giving initial condition, you'll get C1 and C2. Okay. A typical curve probably will look like, this. Go to 0. Okay. Approach 0 infinitely, okay, but not equal to 0. Okay. The bigger the zeta value, what would you expect? Do you think it's going to be, how fast is it going to go to 0? Right? Is when the bigger the zeta, is it going to be slower or is it going to be faster to approach 0? Faster, right? See, the bigger the zeta here, because then the more overdamped it's going to be. The bigger the zeta here, the bigger the lambda 1 and lambda 2 is going to be. So if I draw two curves, if this is 1, zeta 1, then the second one may be going to be something look like that. Okay? So this will be zeta 2. As a second here, am I right? Yeah, I think this is, my lecture notes is not quite right here. Yeah, I think this is right. Yeah. Okay. So that's case number 1 added here. Okay. Yeah. Let's look at case number 2. Case number 2 is when you have 2 repeated roots. Okay, 2 repeated roots. 2 repeated roots means when which term is 0? When the zeta equal to 1. Right? So when zeta equal to 1, then you get 2 repeated roots. Okay. So that's 2 repeated roots. And when you have 2 repeated roots, your lambda, right, let's look at lambda solution. So lambda solution, this term is 0, so lambda will be just negative zeta omega n. So if you then let lambda equal to this, that's basically 2 repeated here. So what's the solution for x of t? According to the table, the solution is c1 times c2 times t and e to the power of lambda here, or which is e to the power of lambda t. Okay, and that's basically e to the power negative omega n t. Okay, that's a solution when you have 2 repeated roots. Again, this value is less than 0. So as t go to infinite, your x of t will also go to 0. And now you might wonder, what about the second term? Second term is t times this, right? This is t times this. Okay. If you recall in the previous lecture, I proved you can use the L'Hopital rule to prove that as t go to 0, this term is also going to 0. Okay. So the whole term will go to 0, x of t. Right? That makes sense. You know, basically, you still have the damping at here. Okay. Yeah. So that's zeta equal to 0 to 1. This one here, we call this is the critically damped system. It's a critically damped system. Okay. Case number 3, okay, is when this value is less than 1. So when damping ratio is less than 1. When damping ratio is less than 1, basically you go back to your solution at here, okay, general solution. This term becomes less than 0. And then you got 2 complex conjugate roots now, right? So when you have 2 complex conjugate roots, your lambda 1 and then 2 can be written as this. So basically we take out the negative sign, so 1 minus this, then you gotta put a j at here. So your lambda are 2 complex conjugate roots. In our table, we call this is alpha and this is beta. Right? In our table, we call the alpha and beta here. Okay. So alpha equal to negative this, and beta equal to omega n 1 minus zeta square root. The beta has a special name for it actually. Okay. The beta is called, okay, sometimes we write this beta as omega d, okay, the symbol wise. It's called damped natural frequency. So this is called damped natural frequency. Okay. Okay, good. So then what's the solution for this case? Right? The solution for the case, if you look at your table, because here you have alpha, here you have your beta. So the solution is e to the power of alpha t, and then times a cosine beta t plus b times sine beta t. Okay, that's a solution, right? You can look at the table, you'll see that's a solution. And a times cosine t plus b times sine t can be written as one single term. And let's call that e times, which essentially square. Oh, we're sorry. What's that mean? Oh. Okay, I guess we lost it. You write them down, right? Okay, good. Oh, I should ask a copy from you guys actually now. So that's good. Actually, if I made any mistake, then it's all gone. Case number 3 is when lambda 1 and 2 equal to this one, and alpha equal to negative omega n, beta equal to omega n times y minus zeta square. Okay. Solution is x of t equal to e to the power of alpha t a cosine beta t plus b sine beta t. Okay, so that gives us e to the power negative omega n t, and the two terms combining together is a squared plus b squared cosine omega dt plus minus phi. This one here basically is omega d. Okay, so the damped natural frequency. Okay. So when you have two complex conjugate roots, and that's when your zeta is less than 1, when damping ratio is less than 1. This looks very different now, because the previous two cases has no sinusoidal component in the solution. But this time, when zeta is less than 1, you have a sinusoidal signal in the solution at here. Okay, and plus this term, okay, in the front as a coefficient. Okay, so what does that mean is the response for x of t, which is essentially the vibration of this mass, right, indicating the displacement, it will display oscillation, okay, based on this term at here, sinusoidal. Okay, so if you draw this out, you're gonna get, okay, x of t more or less look like this. It will still go to 0 because for this term at here, as t go to 0, your x of t still go to 0 because the first term. The first term is exponential decay function. As t go to 0, and this is still going to go to 0, right? Yeah. So that's why you will see a function like this. The oscillation is because of this, and the decay at here more or less like this. So you have a sort of like a boundary of the decay here, and that boundary is given by the coefficients. Okay, so that boundary is given by this portion here because of decay, and the oscillation is given by the cosine, the sinusoidal portion. Okay, so that's the idea of this free vibration. Theoretically, there's nothing new at here. Basically, we're still looking at mathematically a second-order linear homogeneous ODE. Okay. However, when you learn vibration, okay, you basically will look at using omega n and zeta, natural frequency and damping ratio, to study the response of the system. And the response of the system completely depends on the zeta value. You have a zeta greater than 1, equal to 1, and less than 1. So overdamped, critical damped, and then under this case 3 is called underdamped. Okay, so let me summarize a little bit here. And overdamped when zeta is greater than 1. Critically damped when zeta is equal to 1. And then underdamped when zeta is less than 1. Okay? Yeah. So that's very, very common. In mechanical system, you probably, okay, every system has a natural frequency. Okay? Every system can be overdamped, critical damped, or underdamped system, depends on your design. Right? Most of the systems are overdamped when you see a building, okay, especially. Okay? But for a spring, okay, even sometimes spring itself has damping, okay, and that can be an underdamped system. Now the expectation at here is, okay, I need you to be able to identify what type of system, okay, it is based on the given system parameter. Okay, so the expectation is very simple. If you have a second order ODE, okay, given like in this format, okay, can you identify which type of system is this, and what will be the natural frequency? Right. So basically, what is omega n? Okay, what is the natural frequency? And what type of system it is? Is it overdamped, underdamped, or critical damped? Right, that's what it means. So what do? You basically, here you resort to the formula, right? So here is your omega n, here is your zeta here, okay? So you basically calculate those values and try to identify what type of system it is. Okay. Yeah. So let me give you a few examples here. Okay. So let's say, for example, first m equal to 1, b equal to 0, and k equal to 4. Okay. So if you have mass 1 kilogram and damping ratio, damping constant, Newton seconds per meter, stiffness is Newton per meter. Okay. So let's take a look at the type of system in here. Omega n is square root k over m. K is 4, m is 1, so natural frequency is 2. Okay, so that's 2 reading per second. Zeta here will be 0 over whatever the bottom is, so it's going to be 0. Okay, there's no damping at all, right, when zeta is equal to 0. And that's the case, we call that undamped system. Okay. So as a matter of fact, when zeta equals to 0, it doesn't belong to any of this one here. Okay, that's a special one. That's called undamped system. The 3 cases given right here belong to the damped system. Okay, so when you have a damped system, you have 3 different damping. That's three kind of damped response. Yes. Yeah, so this one here doesn't include zeta equal to 0. So this zeta equal to 0 is not included in this case. Okay. When it's underdamped, your zeta still have a certain value. Doesn't matter how small it is, huh? As long as zeta has a value there, then your system will still go to 0 as time goes to infinite. Zeta? Yeah, zeta is always greater than 0. Yeah. That's the definition of zeta, right? So those are all real positive numbers. So zeta is always greater. That's a system parameter. So your system parameter cannot have negative value, basically. Right? You can't have a negative mass, right? You can't have a negative spring stiffness, and you cannot have a negative spring damping coefficient. Yeah. Okay. So that's the system here. Second one here, okay. And if you plot the system, you'll get basically undying oscillations. So let's see if we have another set of parameter. 114. 114. So you can calculate zeta. Omega n will be still the same. Omega n is still the same value, but zeta here now is 1/2 times km. Right. So it's b over this. So 1/2 times square root 4 times 1. Okay, so what does that give us? So 1/4. So 0.25. Okay, so zeta is less than 1. When zeta is less than 1, so your conclusion is this is a underdamped system. It's underdamped. And this value is very less than 1. So even without actually plot it out using computer, you actually should, in your mind, for the response of x of t, so you should visualize there are quite a few bumps up and downs before it settles down to almost 0. Okay? Yeah. So that basically tells you what sort of response you would expect based on the zeta here, right? So let's take a look at one more set here. So this is 1, b is 2, and k is 4. So m, k is no change, but b twice as much, become 2 now. You calculate zeta, that will become 0.5. Okay, so it is still less than 1. Okay, but zeta is bigger than the previous case. So then when you plot them out, okay, and you will see that, okay, see this is the first one when zeta equal to 0.25, and this is the second one when zeta is equal to 0.5. So there are less oscillation now, right? But there's still oscillation, okay? And it's very much close to 0 at a t equal to 5 seconds. Okay, so that's idea how to identify the system here. This is still underdamped. Keep increasing the damping ratio. Okay, now the damping ratio become another damping ratio. The damping constant becomes 4. Okay, so I should correct myself. You actually should repeat. This is damping constant. The zeta here is called damping ratio. Okay? Yeah. And this time your zeta will become b/2 times km. 4/4 becomes 1. Okay, becomes 1. This is called a critically damped system. A critical damped system. So what does a critical damped system means? So if you look at the response, this is the response here. It just eliminates the oscillation. So you don't see the oscillation anymore, right? And you only see exponential decay behavior. Okay. So that's called a critically damped system. If I keep increasing b to 6, and this time your zeta will become 1.5. Okay. It becomes greater than 1. So this becomes a overdamped system. Okay. So overdamped system means it becomes, this is a critical damped, and overdamped becomes basically more sluggish. So if you look at the door, if you have a very high damping ratio there, right, it closes and opens really slow, right? So that's what the damping is doing over there. Okay? Yeah. So this is a comparison from underdamped to critical damped and then to overdamped, right, based on the values of zeta here. Right. So the purpose of this portion here is not really to introduce a new type of a differential equation or anything. Okay, so still the same second order linear homogeneous ODE, but we give it a flavor of a real system. Okay, and how do we describe this real system? Using the parameters of zeta and omega n. Okay. In your third year, when you learn vibration, okay, you will see probably this a little bit again, and your instructor may not derive everything, but it will basically make use of this second order ODE. Okay. Okay, so we have a few minutes here, so let's continue. So up to this stage, okay, what we have covered, as you can imagine, are second order ODE homogeneous without input f of t. So for the rest of the second order, so we're going to consider the rest of the case like this. So let's consider a non-homogeneous now. And we will still consider constant coefficient second order ODE. Okay. And the format of the function looks like this. So A times y double prime plus B times y prime plus C times y equal to a non-zero value f of t. So f of t non-zero, that means this is essentially the non-homogeneous means. Okay. And constant coefficients, so A, B, C, are constants. Okay. Okay, so how do we solve this type of second order non-homogeneous ODE? Right, that's the focus, okay, for next couple lectures. Okay. So let me introduce a symbol first, okay, for the ease of writing. Okay. Let's define an operator. Okay, let's define an operator here. So this operator, I'll define it as L. Okay. Remember we use M, so this time I'm using L here as operator. So this operator you define as A d over dt, this second order derivative, B first order derivative, and then C. Okay. So this is an operator here. So operator basically means whenever you put something in the bracket, it will operate that thing that you have put it into the bracket. Okay. So if you put a y at here, so then you get essentially dy over dt square, and then b dy over dt, and cy. So that's the left side of the second order ODE. Okay. Yeah. So that's the idea of introducing this operator here. Here's the theorem. Okay. What are the general solution, right? This is the idea. We're looking for the general solution for the second order ODE. Okay. So when I write L bracket y equal to f of t, basically it's this one. Okay. It's this second order non-homogeneous ODE. Then what is the general solution for this second order non-homogeneous ODE then? Okay. So the theory says this. First, if let's call YH is the general solution for for this. Okay, so YH is the general solution for L operator Y equal to 0. So what is L Y equal to 0? It basically means what? Means the left side equal to 0, right? Left side equal to 0. And left side equal to 0, that's exactly what we have just learned. It's the what? The homogeneous second order ODE. Okay? Yeah. And we call YH is the general solution for this. So that's fine, because we have learned how to get the general solution for that. So we can get YH based on what we learned. Right? And not finished yet. And let's call YP. Okay, is the particular solution for Ly equal to f of t. Okay. So YH is the general solution for the homogeneous one. YP is a particular solution for the one we're looking for, right? Ly equal to f of t. Then we can make a conclusion now. Then the general solution for this non-homogeneous second order ODE is Y equal to YH plus YP. Okay, this is the theory to guide us through this general solution for the non-homogeneous one. Okay. So let's repeat this theory here. We're looking for general solution for this second order non-homogeneous ODE. And this theory says, first find the general solution for the non-homogeneous one. Okay? Basically let f of t equal 0. And then find a particular solution for this non-homogeneous. And then you add them up, and you get a general solution for the non-homogeneous. Okay? Yeah. So this one we have learned. So that's fine. So we have already we are able to find this half of this term here. Now this one here, right? This is the question mark. We need to find a particular solution. So what will be a particular solution? How do I find a particular solution for this non-homogeneous ODE then, right? Yeah, that's the point. Okay. So the idea is how to find YP. Okay. That's the focus, to find the YP here. The proof of this theory, I have it in the lecture notes. Okay, so you can take a look at the proof in the lecture notes. To find the YP, we're going to use two different approaches. Okay, the first approach called a method of undetermined coefficient. Okay. The first approach we're going to use is called method of undetermined coefficients. And the second method is to use the so-called variation of parameter. And that sounds familiar, right? So we're going to show you two different approaches to find this YP. And then you add up with the YH, the general solution for the homogeneous one. Then you get a general solution for the non-homogeneous. Okay? So these two methods are for finding YP. Okay? So I'll show you the first method, the method of undetermined coefficients, in the next lecture. Any questions? Okay? Thank you.